Hello. This is a continuation of discussion of magnetic fields. I'm going to start with a solenoid where we left off, and I'm going to follow along with this PowerPoint presentation so you can both see me and see some of the slides. And when we get into math, I'll go to another medium so that I can actually write things that you can see. But I wanted to show you this picture of a solenoid. It's the coil of wire, as I talked about. You can see the current going in, the current going out. If you use the right-hand rule and wrap your fingers in the direction that the current would go, your thumb would point up. That's the direction, that's the side of the coil where there would be what we call a north pole. The bottom of the coil, the opposite side of the thumb, would be the south pole. And the solenoid actually represents a magnet just like any other kind of magnet that you'd have at home, a bar magnet or some of the rare earth magnets that you're seeing me use in some of the demonstrations. Those all have also a north and a south pole. And we can create a magnet by basically coiling up a wire like this, and you have a magnet with a north and a south pole, just like the permanent magnets that don't require a current going through them to create the magnet in that case. So I thought this was a useful graph to show you, or a useful figure to show you. You can also see something, there's an analogy between a magnetic dipole, which is what this is. We have a north and a south pole. Of course, you can't have a single north or a single south pole. They always come in pairs when you have magnets. For electric charges, if you have a plus and a minus, you get a similar looking configuration as far as the fields go. That's an electric dipole. This is a magnetic dipole. It's a different animal, but they're cousins, so to speak. They're related, and we'll see how they're related shortly, probably the next lecture. But this is actually also very practical, and I'll be showing you a little demonstration as soon as I get it built. Now that I'm home, I guess I have more time for doing this kind of thing. But if you've ever made an electromagnet, you can basically take a nail or something that's made out of iron and wrap a solenoid around it. That actually intensifies the strength of the magnetic field that passes through the center of the solenoid. And the magnetic field gets attached to that nail. So that nail all of a sudden could become a very powerful magnet if you have enough current flowing through it and or enough coils wrapping around it. That combination can result in a very powerful electromagnet, which is the basis for so many of the tools and things that we use today. Whether it's a speaker or microphone or, relays, there's all sorts of circuits that rely on this type of coil. Coils are so important in modern electronics, in our modern life, far beyond what you might imagine. Any motors, your electric fans, any of that, they have coils of wire in them to help create the rotational motion, and we'll talk about that a little bit more later too. We already talked about this in the last lecture, but I figured it doesn't hurt to see it again. This is the magnetic field associated with a wire with a current flowing through it. That's the equation I gave you earlier in, excuse me, in the last lecture. Mu0 can have a lot of different units. I gave you a slightly different unit. I think I gave you Tesla meter per, see if I get this right, Tesla meter per amp. But it's also equal to a Newton per amp squared. And I'm going to show you in the next slide that a Tesla, which is the SI unit for magnetic field strength, can be expressed in a lot of different ways. Here we see it expressed as a kilogram per amp second squared, or a Newton per meter amp, and the list goes on. Here's a few of the things that it could be expressed at. Some of these units we haven't seen yet, but many of them we have. You've seen a joule before. You've seen an amp before, a meter before, volts, seconds per meter squared. You haven't seen a Henry. That's another unit which we're not really going to talk about. I will mention the Weber, which is this one over here, Weber per meter squared. But we're starting to get a lot of different ways and combinations that we can express these units. But basically the one I want you to know is that a Tesla is a measure of magnetic field strength, and a Tesla represents a very strong magnet. The Earth itself has a magnetic field. It's just, it's fractions of a Tesla, on the order of thousandths of a Tesla. Now, what I want to start getting into is how does a magnetic field affect a charge? And to review that, I thought it would be useful to start with some examples of how, well, I'll get into how electric fields affect charges. Hopefully you already know that, but I'm going to review that because it's different for a magnet than it is for an electric field. So here's a couple of things I'm going to tell you. If you have a charged particle sitting here, and you have a magnet here sitting here, the charged particle will not be attracted to the magnet or repelled by the magnet. The charged particle won't even know the magnet's there if it's stationary and if the magnet's stationary. Okay? Seems kind of boring, and it gets more interesting than that. However, and also, okay, let's say there's a magnetic field going this way. It's going up, let's say. Let's say there's a charge that is also moving, and it's moving in the direction of the magnetic field. Magnetic field is just sitting there. It doesn't move, but it's pointed in a given direction. Let's say the charge is moving this way. Won't have any effect. The charge is moving that way. Won't have any effect. Where it does have an effect, though, is, let's say you have a magnetic field pointed up, and you have a charge moving that way. Then the charge is going to experience a force. If you have a magnetic field pointed up and the charge is moving that way, then that charge is going to experience a force. And what we're going to be talking about is how big is that force and in what direction is that force. And there's an equation on the slide which doesn't look very complicated, except you might get a little nervous because that F is a vector, the V is a vector, and the B is a vector. That means the force, the velocity, and the magnetic field all have a direction as well as a size. Q is the size of the charge, and we're assuming it's a positive charge, but it could be a negative charge too. And if it were negative, everything would be flipped, and I'll tell you about that later. But right now, I'm just going to assume that Q is a positive charge. What this equation is telling us is that the charge is going to experience a force F, and the size of that force is going to be equal to the product of the charge. And this looks like a multiplication between the V and the B. That X looks kind of like a multiplication, but it's not a multiplication. It's actually something called a cross product. And it's a multiplication if V and B are at right angles to each other. So if V is this way and B is that way, then you multiply the V and the B and multiply that times the Q and you get the size of the force. If V and B are that way and they're right angles to each other, you can do the same thing. No matter what the orientation is, if they're at right angles to each other, and my finger, I'm making them always be at right angles to each other, then you can simply multiply the two of them together. If they're parallel to each other, the cross product has a value of 0. So another way to write this, and I'll see if I can write it, is I can write that as being equal to, if you just want to know how big it is and not worry about the direction, it's also equal to Q times V times B. I'm just going to write the numbers there, or the symbols there, without any vector sign on them, but multiplied by the sine of the angle between V and B. Let me make that be an angle. So I have to give it a symbol, theta. There we go. Okay, so in scalar, if I just want to figure out how big that force is, the scalar version of it, the size of it, it's Q times V times B times the sine of the angle theta. That angle theta, remember, is the angle between V, or V and B. These two, B is this way, let's say, V is that way, or vice versa. The angle is going to be 90 degrees. Sine of 90 degrees is 1. If there's 0 degrees, the sine of 0 degrees is 0. If it's somewhere in between, then that size of the sine of theta is going to be somewhere between 0 and 1. That's how you calculate the size of the force that's going to be acting on the charge. Now, that's something you can plug into your calculator. What's perhaps more interesting and maybe a little bit more confusing is what's the direction of the force. This is where we're going to use something called the right-hand rule, which we've been talking about. We're going to use it again. All right? So I'm going to give you a few scenarios, and I'm going to illustrate what the right-hand rule is. There's a couple of ways you can do it, and I'm going to do it with my hand right here. You put your hand, this is how I like to do it. I put my fingers in the direction of the motion of the charge. That's the V. I bend them in the direction of the magnetic field. And my thumb points in the direction of the force.